Hello. Today we're going to talk about Chapter 18, Confidence Intervals for Proportions. All right, so before, when we did sampling distributions, they were normal, right, with a standard deviation for proportions and for means is this. But what if we don't know the population statistics, right? Are we just stuck? Well, no. Okay, we're going to use sample statistics. So based on our sample, we're going to estimate what that population standard deviation is. Okay, so we're going to call that the standard error. All right, so instead of saying the estimated standard deviation of the sampling distribution of the sample statistic, okay, right, we say standard error. All right, it's very similar formulas, right, but notice that we're using the sample statistics. Once we find that standard error, we can get the confidence interval. All right, so then we can still use our old rule, okay? And using that rule, we'll know that 68% of all our samples will have a sample mean within, or sample proportion within one standard error of our proportion. Okay? So think of it like this. So usually we use 95% or within two standard deviations or standard errors. Okay. Here it would say there's a 95% chance that the population parameter is no more than two standard errors away from the sample proportion. Okay. So if we reach out two standard errors in both directions, we will be 95% confident that that interval contains the true proportion. Okay, so based on what I get in my sample, if I go out minus two standard errors and I add two standard errors, standard errors, okay, that is my new interval. So from here to here. Okay, that should contain the true proportion. Okay, so why would we construct a confidence interval? Okay, well, it's very unlikely that our sample mean or sample proportion would be the same as the population. Okay, the odds, we don't know, right? We don't know what it's supposed to look like. Okay. So here, if we create an interval and say, hey, instead of it saying being exactly 5, we're going to say it's between 3 and 7. Okay, that's much better. All right, it kind of gives you like a safety net. All right, so let me try and explain it in another way. Okay, so what does that 95% confidence really mean? Okay, the interval uses a sample statistic to estimate the population parameter. It's an estimate. Okay, we won't know its true value, but we can, give it our best guess, right? It's between here and here. I'll give you a range, right? Think of it like that. All right, now samples vary, so the statistics we use, so the confidence interval will be different from sample to sample, okay? But they should roughly have some overlap, okay? What I mean by that is look at these little like box and whisker plots, or roughly whatever they look like. These are all your different samples. Well, the green line is the actual true proportion. Each of those would construct that interval, that confidence interval, and so you see how most of them are covering that green line, but some of them aren't, right? Very few. So that's our process of how we get our interval. We expect all these samples, 95% of them, all right, would contain the true parameter. Okay, so we're saying 95% likely that it's within this sample confidence interval. Okay? All right, so now just to clarify what it means to, be a confidence interval, here we have a survey. So in the sample, somewhere between 13 and 21% reported they had received texts. Well, yeah, actually, 17% reported yes. So it's true, but we don't need to put the margin of error there. That seems kind of silly, right? We know the exact answer. All right, for part B, we can be 95% confident that 17% received texts. Okay, no, not quite. All right, we're confident about the interval, not about the exact value. All right, that's the difference here. All right, part C, so we are 95% confident that it falls between that interval. Well, that's exactly what it means. Okay, so that's what we want to say. For part D, the problem with this statement is that we know, that's saying basically with a 100% certainty, that's not true. We are only 95% confident. All right, part E, you don't want to say it this way, all right, because that's not what it's measuring, okay? That's not what 95% is. All right, so now we're going to put it in context. Here, we are going to claim that with 95% confidence that the interval is this. So using our sample proportion, it is plus or minus 2 standard errors. Okay, so that's going to contain the true population proportion. All right, that 2 times the standard error is called the margin of error. So what are you adding and subtracting to both sides of your sample proportion? Okay, so we can think of the confidence interval being in the form your estimate plus or minus the margin of error. All right, or the estimate plus me. All right, so here's the key. The more confident we want to be, the larger our me has to be. Okay, so the more confident, the bigger my ego, the bigger me has to be, which makes sense because that's going to create a bigger interval and that's going to make me more certain, right? If I say that the chances of it raining tomorrow is somewhere between 1 and 99%, well, I'm not wrong. Okay. With adding that range, with a bigger range, you're just going to be more certain. Okay, that's the key. Hopefully that makes sense. Okay, so what's better, being more certain or more precise? So would you rather be 99.7% confident, but having this huge range? Or is it better to have a 90% confidence in a much smaller range? What's going to be better for your situation? And that's really what the key is. Okay, I keep saying that a lot. I don't know why. Sorry. All right. A lot of really important parts to this. Okay. All right, let's do a quick example about margin of error. So here we've got a poll that says, do you believe it global warming? 82% said no. That's sad. All right. So what do we do? What is meant by their confidence interval? All right. So how do we write that? Okay. I would write it like this. So if the polling were done repeatedly, 95% of those samples would yield a confidence interval that would contain the true proportion. Okay. All right. In the poll, all right, it's conventional for pollsters to use 95% confidence level. All right. How did they calculate their margin of error? Right? How did they get that 3%? So what do? Well, assuming it's 0.5, right? 50-50 chance of saying, yes, you believe it, no, you don't. Okay, and here you have random sample of 1010. All right. Oh, well, that's what I get for merging the textbook and someone else's example. All right. Because, yep, on someone else's slide, they had Fox News with 900, but this was done, yep, okay. Hold on. Sorry, I figured I'd go ahead and do the statistic. All right, so here, the random sample shouldn't be that. It should be 900. What am I saying here? So this is 900, which means your answer is 0.016, well, 6 repeating, right? Or we could just cut it off at 7 if we want to do 3 sig figs. All right, so then if that's just the standard error, okay, then the margin of error is just 2 times that. So this would be, and of course I messed all that up, so 1.67, beautiful, and then this would be 0.033. Oh yeah, easy fix. It's just a bit over 3%. Okay, and yep, I totally messed up this sentence too. The true proportion of all U.S. adults who believe global warming does not exist. There we go. Now I fixed it. Contain the true proportion of all U.S. adults who do not believe in global warming. Sorry, don't know why. That's what I get for copying somebody else, right? All right, so now we need to know about critical values. All right, actually 95% confidence interval isn't exactly 2 standard deviations away. So if we get out our calculator and we do second vars, we do inverse norm, we want the area to be 95%. Oh, let's see, this calculator is different. Hold on, gotta think different. Oh, what happened there? Okay, so what you want here is you actually want, because this calculator, oh, let me show you. All right, on this calculator, the TI-84, the one that I actually have in class, this one you can put the 95% in the left, center, or right. But on the older calculators, you want, well, we want 95% to be in the center. All right. Unfortunately, those old calculators do this and everything down. So we need to also include this 2.5%. So that's why on the calculator, we need to change this to 0.975 with a mean of 0, standard deviation of 1, and notice what happens. It is 1.96, right? That's the standard deviation, not 2 standard deviations, okay? So that is the critical value, and we'll denote that as Z star. Okay, so Z star, it's that little asterisk above the 8. So, of course, you can do any different critical value. That's just the most common. Or, well, toss up between 90% and 95. So here, you can use that calculator as well to also find this critical value. Okay, so let's practice some more. So going back to our Fox News poll. All right, what would be the margin of error for a 90% confidence interval? I know, pause it, think about it. Okay, so what you would do here is, all right, you'd label what N is, what your sample proportion is, plug it into your standard error formula, bam. For a 90% confidence interval, your critical value is this, So either say critical value or label it Z star. Don't just put these numbers down. See how everything is labeled? That's what I'm expecting. All right, then the margin of error would just be those two multiplied together. Bam. So the margin of error here would be just a little over 2%. Okay, so plus or minus 2%. All right, now if Fox wanted to be 98% confident, what would happen to their interval? Be narrow or wide? Well, if I'm going to be more confident, then my interval is going to be wider, right? Because then I can't be wrong, right? So here, let's see if they reduce the margin of error. So if we squeeze the margin of error, I kind of gave this one away if you think about it, the confidence would be lower. Okay, that's what happened up here. We decreased it to 90% from 95, and the margin of error got smaller. What would happen if I polled more people? Well, then my margin of error would become smaller, right? Because that's what I'm dividing by. So if the number of people increased, then my margin of error would get smaller and smaller. I'd become more and more accurate. Okay, so all statistical models make, All statistical models are made upon assumptions. That's clearly a typo there. That's supposed to say made upon assumptions. Different models make different assumptions. So we can't be sure if the assumption is true, right? Because if it's not true, then things are all wrong. But we can check it based on conditions, okay? Assumptions are exactly what that is. They're plausible. Okay, so the first assumption is the independence assumption. So again, you can't just look at the data and tell. You have to think about your situation. All right, so you can check it based on the randomization condition. So what happened to the sample? Was it randomly generated? How was it done? Okay, it varies from study to study. The 10% condition, so the sample size is no more than 10% of the population, right? Especially those surveys. Think about that. If you survey more than 10%, then you could possibly be double counting people, right? You're getting too many people to volunteer, okay? And you don't, if you claim to get 50% of the population, well, I don't know, your sample might have been couple people doing it over and over again. Okay, so that's why they have that rule. Well, I don't know. That's what I think about anyway, or how I justify it. Okay, so the sample size assumption. So the sample needs to be large enough for us to be able to use the central limit theorem, which is, of course, when we have 10 successes and at least 10 failures. Okay, because if you are expecting so few, well, then your whole thing's not going to turn out to be normal. Okay. Okay, so now we can get our confidence interval, and we can get them with a 1 proportion z interval. All right, also using this formula. Notice your standard error formula based on your sample statistic. Of course, your critical value is your z star. That, of course, depends on your confidence level, so that just depends on the situation, right? Think about it, 90%, 95%, that's what you're looking at there. All right, I get this question all the time. How large should the sample be? Well, I don't know, right? It depends. It always depends on your situation. But one way we could figure it out, mathematically, is by choosing our margin of error and a confidence interval level. So, let's see. So basically, we're going to plug these values in and then solve for n, okay, where n is the number in our sample. So here, we're not really sure what our proportion is going to be, right? Our sample is, right? Because we don't have our statistic, right? We don't have our sample size yet. So we can just estimate it by using 50%. Okay, that's going to give us the largest value for P times Q. Okay, so that's going to give us the biggest sample that we could possibly need. Okay, I get it. I know I'm confusing sometimes, so let's do an example. So here, back to our Fox poll. So how large of a sample would they need to reduce their margin error to plus or minus 2%? Yes, I know we saw this, but let's just look at look at it from a different angle. Okay, so we set up our formula. So this is what we want. We want that margin of error to be 2%. We wanted it for a 95% confidence interval. We don't know what N is, and again, using the wrong stuff. Okay, now I fixed it. So here is our critical value for 95%. 82% believed in global warming. I'm sorry, didn't believe in it. Okay, well, whatever. 0.18% said it the other way, and then we solve for N. So literally getting all this stuff to the other side. So divide by 1.96 and then square it. So let's see. Then you square it, and then that would equal 0.82 times 0.18 all over N. So all you would need to do is in your calculator go and put N is just going to equal that 0.82 times 0.18, and then make sure you divide by this entire thing. So make sure you're putting in all your parentheses. So this still had parentheses, and then you put parentheses to end it because that's what the denominator is. Okay, well, I guess you didn't quite need it in this case. Well, you guys get it. Okay. So that's how we can solve for N. Just wanted to go through that just to make sure you guys understood the math. All right, if that's still confusing, just come talk to me. I'll walk you through it better. Okay, but N should end up being rounded to a little over 1,400 people. All right, so let's do this example. So they're sending out, going to send out a mailing to test the market for a new credit card. Okay, so mailing flyers and stuff. All right, so we get this information. How big does the sample need to be? How big does this test need to be? So make sure you set it up correctly. It said within a 1/10 of a percentage point, so that's the margin of error. 1 percentage point is 0.01, so a 1/10 would be 0.001. Make sure you understand that. Your critical value is 1.96. You want 0.5%, so watch the decimal there. And then the other would be 99.5%, and then you would solve for N. So here it'd be a little over 19,000 people. Okay, so that's how big the test mailers need to be. Okay, so let's actually do one on our own. So on the new TI-84s, they have, I think it's in an apps or program, they have a probability simulator that lets you flip coins and roll dice and do all this cool, fun stuff. But, you know, most of us have those old school, right? So let's see, like the original TI-84s and the 83s. So we want to flip a coin 50 times. And using that sample proportion, create a confidence interval. Now, since it's flipping a coin, we know what the true proportion should be, but we're going to use a sample. Okay, so what you can do is, let's see, there might be an easier way, but this is just what I know. We're going to do a random integer generator, and we're going to be 0 is tails and 1 is heads. Okay, because that's what we want is heads. And then we're going to do it 50 times. Okay, So then I randomly selected a number, or I'm sorry, the calculator randomly selected a number 50 times, and I could just go back and forth and literally count all the heads and tails, or I could store that as my list. So second one, so now it's stored as my list. If you don't believe me, go to your list. There it is. Okay. And then you can go to stat. Wait, is it stat? Yes. So do your one variable statistics on your list. And then your sum is 26. So in our sample, we had 26 heads. Okay. So using the random generator on my calculator, so using the random integer generator on my calculator, my simulation yielded 26 heads. Okay. All right, so now we need to find that margin of error. So to find the margin of error, we want to do a 90% confidence interval. That is 645, I think we found on the calculator on the other slide. Okay, so so we need to, I need to label things. Ooh, because this is what I get onto y'all for doing. So since a 90% confidence yields a z star of 1.645, so to get the margin of error, we need to do 1.645 times the square root. Well, we yielded 26 out of 50. All right, for getting a head. For getting a tail, we would have gotten 24 out of 50 out of 50. Okay, you do the proportion over the number of times it happened. Okay, so that's your margin of error, which comes out to be 0.116 to blah, 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 blah. All right, so rounds to 0.116. So now our p hat, so in our sample, it was 26 out of 50. So that was 0.52. So I could have written that there instead of fractions. So our confidence interval is we're going to take 0.52 and add our margin of error, so 0.116, and that's going to get us 0.636, and then take 0.52 and subtract our margin of error, and that's going to get us 0.404. So our confidence interval, okay, we're 90% confident that the true proportion, or that this interval captures the true proportion. So we're saying the interval is from 0.404 to 0.636. And since we know that the true proportion is 0.5, well then yeah, we definitely captured it. Okay, now this would be a cool part if we all talked about our different proportions. Okay, we'd all see what we got. Okay, so it'd be interesting to see because 95% of the samples should be or should capture the true proportion. Okay, so some things that can go wrong. Okay, don't misstate what the interval is. All the time I get kids that keep wanting to add and write paragraphs in their free response questions because they want to show that their knowledge, but then they twist their words and they start misstating what interval is. Okay, so don't suggest that the parameter varies. Okay, the true parameter does not vary. Don't claim that other samples will agree with yours. Don't be certain about the parameter because we can't be certain. Okay, it's not about the statistic. It's about finding the parameter. That's what a confidence interval is. We don't care about the statistic. We're trying to capture the true proportion. Okay, and don't claim that you know too much. All right, statisticians are not, they're not supposed to have big egos, right? Because we don't know everything, right? We approximate, we estimate, we observe. Okay, we can't be certain. Do take responsibility for the uncertainty, so always list your limitations and treat the whole interval equally. Okay, the margin of error, too large to be useful. Okay, so don't make the margin of error. This is, we talked about this before. If the true proportion is 50% or 0.5, you don't want to say, well, it's somewhere between 0.1 and 0.9. Oh, great, you really narrowed it down for me. Thanks. Okay, so we can't be exact. And so we can't be exact. So how precise is that? It always depends. Okay. So think about your situation. It always depends on your study, right? Think about this when you design your study. Okay. Also make sure when you're choosing your sample size, this is another way of doing it. So this is the equation in reverse. So this is another way of going about it. Okay, so of course, to be safe, you always want to round up on your sample size because we're just, this is an approximation. Okay. Watch out for your bias samples. So keep in mind of what you learned in chapter 12 with all those biases in surveys, and always think about your independence. You need those assumptions to be good. All right, and this is what we've learned. So this is just kind of like a recap of everything. One of my favorite cartoons. Hopefully this made sense. I will see you in class if it doesn't.